Okay, hello. Um, the plan for today, so I'm going to finish off. So last week I looked at flexure. I'll go through that first. So your steps for flexure, and yeah, pretty much figuring out phi mu, which is the ultimate moment capacity. And then this week, I'm going to cover like the last part, which is designing a concrete section from scratch. So let's say you have like you only have your loads that's acting on your beam, your structure, whatever, and from there you're gonna like work backwards to figure out your section that actually works, right? So you got to figure out what the depth. So if this is my concrete section, you got to figure out the depth, the width, and the steel required as well, if there is any compressive steel as well. So you got to figure out these. They're not given to you. In an exam scenario, I don't think they can ask this because it takes so long. Like one question by itself will take like 1.5 hours maybe. Yeah, and so it's a really long process. Like I've kind of summarized the steps a little bit, but you can see that there's a lot to it, right? So after design, I'm gonna move on to shear, which is a bit easier. And the theory itself is going to be explained by Henry in his video, right? I want to briefly touch on it, but I don't really like it, so I'm not going to explain it. But Henry explains it way better as well. So, and pretty much the steps. So I didn't actually fill this in. I will. And yeah, the thing about shear, it's like a bit techie. Like there's so many equations that look really weird, but in reality they're really simple, right? Okay, starting off. I'll start with design. So as I said, design steps is when you're given the load and you have to figure out your concrete area, pretty much your base times your depth, all that kind of stuff. And you're gonna have to do a bit of guessing. It's a bit of guess and check work, right? So first things first, you figure out from your loads your M star, right? M star being your critical moment, so your maximum moment acting on the beam. And then we're gonna guess a value for D. So we're going to take some value between ln over 10, ln over 8, right? So what ln is, it's our clear span, which means if we have like a beam like this, can you hear that? Fuck. Shit. Sounds like a mad piss. So let's take a look at the distance between center. So this is my length, center to center, which is usually just our length. But our clear span is going to be the distance from the interior, or like between the interior edges of your support. So they will usually give you like the width of this support, right? From where you can like kind of back calculate and figure out what ln is. Yeah. So in like a real scenario, it wouldn't look like that. You'll probably have like a continuous beam like this. Right, and it just keeps continuing on. And then normally you'll take the maximum span, the greatest span, because your greatest span is going to be your most critical one. What that means, if the longer the span, the more prone it is to failing, which kind of makes sense. If I take like a card, so if I take my student card like this and like squish it this way, or like apply a load to it, it's a bit more stiff. Okay, it doesn't bend as much. However, like this, it bends a lot more. Think about a ruler now. It's going to bend way more. Right? Okay, cool. And then from there, once you find D, you're going to calculate your web width. And what I've done actually, I've got like a list of steps down here. But before that, I'm going to explain the resizing formula. So resizing formula is pretty much, it's just a rearranged version of your ultimate moment capacity. So this is assuming that phi mu is equal to m star. Actually, this, and then you plug in your values for like your formula for mu, and you rearrange for bd squared, right? Bd squared, because later on what we'll do is we're going to guess for b. So we're going to guess for this value b, and make it in terms of D. So what you end up getting is a cubic. This is why I say you can't, they can't really ask you this in an exam because you're solving cubics, right? Am I still recording? Yes. Okay. Is it picking up my mic? Yo. Yeah. Okay. Good. Okay, my pen actually just stopped working. This is great. Give me a sec. Okay. Cool. The actual theory behind how these formulas came about, don't need to know, right? I've kind of explained it in simple terms. But pretty much the steps are going to be calculate gamma, alpha, Ku. You're going to assume for Ku being 0.25. So if you remember from last week, Ku is your ductility. When it reaches 0.6, that's when you have like ductile failure, which is, no. We want it to be less than 0.36 because that's a ductile failure. If it's like less than 0.25, I think there's like a different mode of failure, which we don't want. But yeah, the main...
So is KU the same thing?
Similar.
Oh, okay.
Yeah, pretty similar.
Okay.
KUO is just, I think it's the same thing, yeah.
Okay.
KUO, we call it KUO because we have, fuck, let me go back up. We have KUO, which is equal to dn over d0. KU is just dn over d,
Okay.
which honestly is the same thing.
Okay.
D0 is just distance to the outermost steel.
Yeah.
D is just the average thing. But if it's just one layer of steel anyways, it's going to be the same value. So it's very similar.
Yeah.
But anyways, you solve for D, and then you're going to calculate your depth. So this is like, because engineers were really conservative, we add an extra 65 to account for cover. Yeah, so pretty much what I've calculated first. This is my concrete section. This is my steel. Let me move it up a little bit. So D is going to be distance to the compressive fiber to the center of the tensile steel. And the 65 pretty much just covers for this. That's our cover. And then we're going to round it up to the nearest 50 because why not, right? We're being conservative. And then after you round it up, we're going to recalculate our new D value, this D value. Yeah? It's really weird. But obviously when you're sizing up concrete, you don't want any like finicky numbers like 561.68 millimeters in depth. You want something standard like 650 depth, like 600 depth, something like that. That's why we just round it up to the nearest 50. All right? And then once we find our new D, capital D, so let's say D new, the cover we're going to assume it stays the same. So D new is going to make it to D new plus 65, and you're going to have to calculate D new. Yeah, it's like an iterative step, right? And then from there, you're going to calculate your new B value by chucking it in up here. Okay, so we have B up there, BD squared. Because we know what D is, we just calculate what B is. Or you can, sorry, don't use that, so use 0.5 D. Sorry, use this assumption that we made. Yeah, you can put it in here, but why would you do that when we've already assumed it's 0.5 D, yeah? And then you're gonna have to recalculate M star because that's if, okay, I'm not sure if you guys know. Let's say I've got a beam like this with a UDL. I don't know if I have time to go to a question, but let's say the loads they've given us in KPA. Do you guys know how to convert this to kilonewtons per meter? No? No. So KPA is, it's a load. It's a pressure, right? But kilonewtons per meter is a line load acting on the beam. So it's a bit weird. KPA we usually use for slabs because slabs are like it has an area, right? But for beams we just assume it's like one line. So I have to do it on my iPad. So usually for slabs like this is 3D view. You have like a KPA load which goes along within the whole area. if that makes sense. And then what we usually do, we kind of assume it to be like something like this. But to convert it to a line load, so from a kPa to a kilonewtons per meter force, there's a step. What do you multiply by? It would be like this length here. Yeah. Yeah. But I guess that's not too important. But pretty much what you're gonna have to do, you're gonna have to recalculate your self weight, because self weight. Let's say they give you like the density of concrete is 25 kilonewtons per meter cubed, right? You're gonna have to calculate the self weight using the depth of the section, which has obviously changed, right? So D and DW is updated. So yeah, this is a bit of like finicky pasta, but I don't think it's that important. But yeah, but this is pretty much the steps. If they give you kilonewtons per meter load, then you don't have to really calculate it. If they already give you self weight and everything like that, but this is if they haven't given you self weight. But you're still gonna have to recalculate M star because your loads have changed, right? Because yeah, your flexural span would have changed. Okay. Anyways, now that's designing the concrete itself. So we've designed, out of the RC part, we've designed the concrete, like this part here, the concrete matrix. Now to design the steel area, you guys might know initial sizing from steels, right? It's very similar, very, very similar. Yeah, it's probably a lot of bad memories, but it is very similar in the sense that the equation is you have the load up here, and you're dividing by Fy times some sort of factor. Right? So for compression, it was like 0.4. For tension in steel, it was 0.9. In concrete, it's a bit different. So we have M star, obviously, because we're designing for flexure, divided by phi, which is usually 0.85. Fy is 500. That's the steel yield strength. D is going to be the distance to the center of your bars. J is just a factor. It's really weird. And there's three different cases. If you have a rectangular section like this, it's going to be 0.9. If it's a T-beam at a midspan, so what that means is, let me go back to my continuous case again. T-beam at a midspan just means this part here. Right? That's the middle of the span. Makes sense. At the end of the span, or like at a support, it's actually incorrect. But let's say this isn't a span. Let's say this is just a beam, like this. So this is not a support. These are your supports. So it's a bit weird. You can have supports here, and then like a T-beam, like a slab with like a beam just under it, which forms a T-beam. No, it doesn't really touch the ground, yeah. So the way it would normally look, so imagine, I think that was a pretty good drawing actually. Let me go back. Yeah. So, I forgot what they're called. They're like a certain type of slab. Fuck, I swear I've done this already. Like raft slabs, essentially. Waffle slabs. But anyways, like pretty much over here, let's say this is soil, right? These are like your supports on whatever. And then just in the middle, I might have to give you guys a top-down view. Support. So this is for a slab. Even though we don't really work with slabs in this course. Right? Let's say you've got like a beam here. The dotted line just means it's underneath. Oh fuck, it's really hard to visualize at the moment. Especially for this course. But yeah. If I take a section cut here, so what's going on is I have a slab, so I've got a slab, I've got a support, Fucking Henry. Sorry. And then yeah, pretty much. Oh fuck. What's going on here is like if I cut it here, like I've got a beam here, here, and here. So actually, this represents the beam. Is that going into the page? I don't even know how to explain this. Holy shit. But anyways, like this is the T section here, if you can imagine, and then at a support, the T section would look like this. So it's more of an L section. Yeah.
The side view or the?
This is like a section cut like this.
Oh.
Yeah. So I've taken a cut here, and I'm taking a look at it from here now.
Oh, okay.
Yeah. So imagine this table. I've cut it this way, and I'm looking at it like this.
Oh, okay.
Yeah. Alright, the details of it doesn't really matter because they will usually ask you a rectangular section anyways, right? Or like a T-beam midspan. If they'll tell you in the question as well, if it's a support or a midspan. Okay, after this, so this is your initial sizing. You figure out a certain value for AST, let's say 100 millimeters squared. Yeah. Then you're gonna recalculate, or you're gonna calculate your compressive depth of concrete. So if you guys remember from flexure, this diagram here, this is the concrete compressive strength depth, gamma dn, after you apply your rectangular stress block factors. And you're going to use the value from AST up here. Yeah. And everything is the same that we already know. B for a rectangular section, if you have T-beam at a midspan, so this you'll see actually in your quiz, assignment 3. In assignment 3 you have a T-beam like this, and they give you BEF to be like this, okay? Where this is BW, meaning B-web, okay? Which for a support like this is BW, which is what you'll use. Alright? And now, after that, you pretty much have like a more accurate compressive depth of concrete. And now you're gonna figure out your adjusted steel size. Sorry, let me mute myself real quick. We're back. So adjusted steel sizing. Now you're gonna use a more accurate equation. So this is more of like a Bodgy equation, more of like a just a good starting point. This, as you guys can see, you guys might remember phi mu. You take moments about neutral axis, or this or that. In assignment 2, you figure out another way where you do AST times AST times Fy times d minus gamma dn on 2. Yeah. This is if you have only one layer. If you only have tensile steel, not compressive steel. So actually, no, it works for both, I think. But yeah, essentially you'll see it in your assignment 3 as well. I've made solutions for them, but what's going on here? This is what your stress diagram looks like, with concrete force here, tensile force here, and then you're taking moments actually about this point here. Yeah. So when you take moments about that point, your tensile steel goes to 0. Oh, actually no. What they've done is they've taken moments about here. I'm just kind of trying to show you guys where this equation comes from. And then this force goes to 0, and the distance between here and here is d minus gamma dn on 2. So, and we know this is equal to AST Fy. So if you do moments about that point, you get AST Fy times d minus gamma dn on 2. Might not seem that obvious right now because I don't have a lot of space to explain it. Maybe I will explain it. I've explained it in my solutions somewhere, but I think it would be good to explain it.
Isn't it just taking notes about the basic compression?
Yes, exactly. So I'm going to draw the diagram again. So this is my stress diagram. Just gamma dn, and then you have TS. Right? So this will be CC. This distance will be gamma dn on 2. Then you've got tensile steel, ASTFY, and the distance from here to here is D. Okay, so the distance between here and here is going to be D minus gamma dn on 2. Does that make sense? Yes? And then if I'm taking moments about this point here, the only rotational force is this one here. So because I know m is going to be F times D, where F is AST Fy, and D is just D minus gamma dn on 2. With being the lever arm. So that's how you get mu. This is like a more general equation that we actually use in the industry as well. And then from there, if you assume that phi mu is equal to m star, so you're saying phi AST Fy D minus gamma dn on 2 is equal to m star, and then what they've done is they've just rearranged for AST. That's pretty much where that equation comes from. Okay, I didn't really want to explain about OCD. Okay, and that's your final steer area that we're going to be using. There's like a table that I showed you guys a couple weeks ago. No, that's not right. Okay, I don't have it here for some reason, but the steel area, we're going to be using, it's on your formula sheet. There's like a section at the bottom with like your bar size and your diameter and the number of bars, and it gives you your steel area. Right? And we're going to be using the closest one. But a question, let's say my AST is 1168 nm squared. And let's say one of the options is like one of the options on the table is 1100, and the other option is AST is 1400. Which one would we use? Which one is correct to use? This one or this one? Let's say this is what we've calculated from here. And in the table we've got these two options. Yes, exactly. You would want the bigger one, because this is just not enough. So this, what we have here, is actually the minimum steel area that we need. Yeah. That's why it's greater than or equal to. So sack this, we're going to go for the higher option. Obviously you don't want to go too high. There's like a, it's more, yeah, you just don't, like, if I have like 1168, I obviously don't want to go 2000 when there's an option for like 1300, something like that. So it's a bit of common sense, like here. Okay, a few design checks now. So this one I actually didn't fill out, but I'll show you guys on your formula sheet. Brother. Okay, it's fine. So the actual table of values for the steel area, I'll show that first. So that's at the bottom here. So if I had 1100, I wouldn't go for this, I would go for 6 and 16s instead. It's quite a lot actually, holy shit. Okay, so let me scroll back. So, beam spacing requirement, check half the distance between the two beams greater than 0.1a. There's a drawing for this, but I don't, it's not that important. Usually it is. Right. There's an explanation in Henry's video, he explains it pretty well. I don't have it drawing with me, so I can't explain it right now, but yeah. This is the minimum steel requirement. So minimum steel requirement being, what we calculate here is the minimum steel needed to resist the moment. But this is just a rule, just a minimum steel just required for concrete, right? Just for your strength. And we've got this is the equation itself, right? and you've got alpha B, which has 3 different cases, which I've got here. This is from the formula sheet. So you've got 0.2 for rectangular sections, which is usually the case. T sections where the web is in tension, it's a different case, which is a bit more techy. Flange in tension, a slightly different formula. I've never had to use this before, luckily. So yeah, just hope you guys don't get it. But in general, everything else is pretty much the same. Fy is 500 MPa. BW is a web width. D is just the distance to the tensile steel. Everything else is the same. Yeah. And FCTF I've got here. Yep. And so if the AST that you've calculated is greater than this, you're good. Okay. If not, then you gotta adopt this. Does that make sense? Okay, so the AST that I calculated up here, let's say I've got like 400 millimeters squared. And then over here I figure out that, so this should actually say AST. Let's say I've calculated AST min, which is this, to actually be 600 millimeters squared. So what I actually have is less than what the code says, right? So in my design, I gotta use 600 millimeters squared. So which actually works because 600 it resists both the moment and is satisfied what the code says. Yeah? So it's all good. I just realized maybe there would have been a better way to do these checks, because I had to do a bunch of these checks for advanced concrete. Sorry? Yeah. This is weird because, like, yeah, it's pretty much how they teach. Like, you figure out like what steel you need to resist the forces, right? And then you check if it meets the code requirement. But like, we didn't go this techy into it because everything was a rectangular section, so we just assumed this was 0.2 the whole time. Okay, ductility requirement. So again, this is very similar to what we did for flexure. So check ductility. You just gotta make sure it's less than 0.36. Yeah, pretty much the same formula. This is pretty much equating CC and TS. CC being alpha to F dash C gamma D and B, which is equal to AST Fy. You just rearrange for gamma D N, which is what you get here. And this is actually something. Oh, this is actually something the whole assignment 3 covers, which is really, really good. This is a bunch of ductility checks. And then after you do your ductility check, obviously you've got to do your final strength check, which should be fine. But yeah, you obviously got to check it. So Fy is easy, AST you figured out yourself, gamma DN you calculated up here. Fuck. And yeah, you just check if it's good. So this question itself takes like more than an hour to do. So it's like a bunch of like back and forth. That's why it's a bit hard to understand. I think they have one question in the workshop that goes through it. I'd say flexure itself, like when they give you everything, is way easier. Yeah. Like this stuff is way easier. Yeah. Just pray you get like one layer of concrete. If you get one layer of concrete, it becomes even more simpler. Okay, cool. So that's designing a concrete section, reinforced concrete. Now I'm gonna move on to shear. So as I said, the theory is going to be explained by Henry, but the general principle is you have a shear force at a critical point. This doesn't mean the maximum shear force, by the way. So this is not max shear force. Yeah. The reason for that, the reason why we don't really care about maximum shear force, this is like my understanding of it, but it should make sense. So let's say we've got a beam again like this. With like a load like this. The shear force itself, diagram will look like this. So the maximum shear force occurs at the support. However, at the support, we've got like a column or like a support, right? Which means there's like a bit of rigidity. So cracking doesn't really occur at the support. Cracking is more prone to occur like here or like here, like somewhere here. Yeah? So what we do is we take a distance from the center of the support away, like somewhere here, and that's where we calculate our V star. So it will be somewhere here. Yeah. Because that'll be the critical section. Yeah? And that distance isn't some random distance either. The distance is going to be, let's say this is my concrete section. It's going to be a distance D away, where D is the distance from between the top part to the center of your bars. So it's from the compressive fiber, so up here, to the center of your bars. So it's D, or D0. Yeah? So we take that distance away from the support. Yeah, and then this part is what you gotta do calculations for. Alright? Phi is not 0.85 anymore. For shear, it's actually 0.75. And VU has three components. So there's another component here, which is pre-stressing, but it's not covered in this course. So we only care about the concrete capacity and stirrup capacity. Stirrups being, I'm not sure if you remember, if this is our section, we have stirrups like this. Those are stirrups. Yeah? So those are what we call transverse reinforcement, shear reinforcement. Stirrups is another word. Fitments is another word. That's what they are. Yeah. Okay, cool. Now steps-wise, I haven't filled this in, but I've kind of explained to you that the reason for this is because I'm a bit confused myself about this. There's something called a shear envelope. I think that's just by envelope. Pretty much your shear force, it's not just your shear force diagram, it's a bit different. So for the case that we looked at earlier, we might have like a live load, dead load situation going on. And your shear envelope would actually look a bit different. So your shear force normally would look like this. Yes. I think I can figure it out right now. But this is what your shear envelope actually looks like. It's a bit weird, but there's a reason for this, which I actually don't 100% know myself. I somehow got away with like doing this and still getting it right. It's like, oh fuck, what was the reason? So you've got a dead load, you've got a live load, which gives you an ultimate load. At the face of the support, the way I did it is just, I just use these equations to figure it out. But there's actually a proper way to actually figure out your envelope, and the basis, not really the basis, but like the steps to it is usually like this. Let me show you. So you gotta take this as one load case. The other load case you gotta take like this. And then you add an extra load on top of it, being like your live load, dead load. So you add half the force to one side, and then your third load case you take on the other side. So you take halfway through here, something like this. I'm not sure. Okay. Yeah, that's the thing. And then you add all three shear force diagrams together. Henry has a really good explanation on it. That's why I don't really want to tainted, if that makes sense. Yeah. I feel like he's got a really good explanation. He's making one this year as well, but I think this year's one will be better. But the one that he used, not last year, the year before, was really good. So I'll kind of show you his notes for it. And he goes through a lot of content, which is good. You see something like a truss analogy, which kind of explains stirrups, but like it's not that important. So you find the max shear at the face of the support. So here, you find the max shear at the midspan. So you kind of separate. So you have a dead load, then you put your live load on the left side, then you put on the right side as well. And then you add them up. Fucking weird, bro. I actually don't know why you do this, because usually shear force, I actually haven't done that much concrete to talk about it, but yeah. So your end goal is to develop a shear envelope, and then once you figure out your shear envelope, you want to find the shear force at a distance of d0 away from the face of the support. Yeah. So this is the face of my support. At a distance d0 away, that's what my V star is going to be, and that's the one that I'm going to be using up here. That's my design shear force. Okay. Right. That kind of explains that part. Now the rest I can explain properly. Right. So the first step is finding VU max. So this is the maximum shear force, and making sure it's greater than what's your design critical shear force, right? This is the formula for it, 0.55 times F-C. BV, in this course, is always going to be equal to BW, which, if you have a rectangular support, this is rectangular section, this is just BW, it's just going to be B. All right. DV is the maximum between 0.7 D, where D is the depth of the section, and D, as I said already, distance to the tensile bars. So it's always a bit trippy, this D. So it's from up here to here. Now theta V, in an exam, I think they'll always ask simplified method, which means theta V you can always just assume to be 36 degrees. Yeah? But if they don't tell you to use a simplified method, there's a detailed method, which means you gotta find epsilon x over here, which follows this formula. So you need V star. That's why we tell you to find M star at the start as well. Over here, we tell you to find M star as well, which is pretty easy for this case. It's just WL squared on 8. Do you know that? For a simply supported beam. So if you have a simply supported beam like this, with a UDL like this, W star, your maximum moment is going to be W star L squared on 8. Yes, that's a good thing to know. But yeah, you got to figure out M star. DV is the same thing as up here. Plug that in, whatever, and then you sub this back into here to figure out your detailed theta V. Theta V, it's a bit weird to explain. I think he's got it here. Here it is. It's like the inclination of your compressive strut. So this is like a compressive strut. It's this angle here. Yeah. But this is just an analogy. There's actually no compressive strut like that. It doesn't exist. But it's meant to represent the concrete part there. So, and they've kind of simplified it because it experiences a force going that way and this way. It's like a diagonal thing. The analogy, I'll be honest, hella stupid, but it does make sense. It doesn't make sense to me, but some people say it makes sense. Fuck it. Okay, and then after you do that, so you figure out, you sub everything back in. Yeah, you gotta be a bit careful in your calculator, but then you just check it. If that passes, happy days. Usually it will always pass. If not, wraps. Yeah, I think you're gonna have to increase your B value. Yeah, which I don't think they'll do that to you because they don't expect you to like figure out, oh, what do I do now if this fails. They just want you to check if it works, and it does usually. Next thing is ASV min over S. So ASV is something I haven't really covered. This is the area of your fitment. So for something like this, if I have like use N10 bars, right, that has an area of like 10 squared times pi and 4, 2.5, and fucking like 60. Is that right? That's what it should be. 80. Fuck, close enough. Right, 80. But oh yeah, so the thing is, you don't actually want to calculate anything here or here. You want to just figure out this part, and then you say, oh, okay, ASV min over S is equal to some value. This will come, like, it will be useful later on, right? But yeah, you figure this out, and then next thing is VUC. So VUC is your concrete capacity and shear. That's what we have to see. There's two cases, right? We have VUC is equal to KV times BV dV F dash C. This part's really easy. KV, there's two cases, right? We've got ASV over S being greater than this value up here, or it's less than what's up here. How do we know which one it is? We don't. We're going to assume, okay? So we're going to assume this first. Okay. If this works, then we'll just keep it as it is, right? So in the next step, so actually, let me talk about this. This is the same epsilon x as what we had earlier. Oh, another thing is, by the way, if you have simplified method, I forgot to write this. KV is equal to like 0.15. So you don't have to go through all this bullshit. They'll just give it to you if it's simplified method. If they don't give it to you, if it's not simplified, if it's detailed method, you don't have to check which one. Meaning, assume this first, and then you do your test. Usually what happens is, if it doesn't work, we just add stirrups. We don't check the second case. It's like too much, right? Yeah? Because we're the ones designing the section, right? So we're allowed to actually like determine what's going to happen with the fitments and whatnot, right? I hate Shear. Add stirrups. So this is a bit of a weird part. So always calculate this part first, which is our right hand side. And we're going to assume a spacing, right? You're allowed to do that because, again, we're the one designing it. So we're allowed to put the fitments at a certain spacing, right? Usually somewhere between 200 to 300. 300 is pretty normal. So you can assume a spacing, be like, oh, okay, assume 300 spacing, and then you figure out ASV, right? Sorry, which assumption? This one? Up here? This one? It affects your strength for your stirrups. So how much capacity it provides. Because if you think about it, because this is the capacity of the stirrups, right? Which is a function of S. So if we increase that, it's going to decrease. Like the amount of capacity we have decreases. Which kind of makes sense because imagine we're looking at a beam from the side, right? We have stirrups every 300 compared to stirrups every, let's say, like 200. Obviously, there's like more stirrups here, which means it provides more capacity. That's why 250, 200. Actually, you know what? This thing. It's really weird. Hey, I'd say safer to assume your spacing first. So somewhere between 200 to 300, and then you calculate ASV. So again, when you actually figure out ASV, it might be like a weird number, like 200, like 200. Oh, no, that's not good. 238. Who's calling me? Oh, talk to him, but something like this. Again, you're gonna have to like round it up to something. So maybe like 240. So instead of instead of 238, I'd use 240. Alright? And then that's the value we use down here, along with the spacing that we assumed. This part, it's a bit iterative as well. I think next week what I'll do, because me explaining it doesn't make any sense, I'll go through a question first to kind of explain how this part works. Because right now, even I'm confused. Yeah, I'm not really confused, but like the way I'm explaining it doesn't make sense without an example. And I have not prepared an example, which I should have. Yeah, I'll do it next week for sure, because we're running out of time soon anyways. But yeah, it's actually not that hard. Like shear, like once you tackle this part, it's actually really easy. Like everything else is like pretty chill, if they give you a simplified method. If not, GG's. But yeah, oh, by the way, another thing is, if this passes, so if this is true, so obviously if your capacity is greater than V star, we don't need stirrups. Stirrups is only needed for fails. Yeah? When we're designing something, we add stirrups anyways for robustness. Yeah? Which just means like just to be safe. And yeah, pretty much this is your. No, wait. This is the final check at the end, but I should have added this at the very end. But before you finish off your calculations, you're gonna have to do some detailing checks, right? Which means your spacing is fine, your web crushing is fine, whatever that means, and your minimum stirrups check that we assumed earlier, right? So max spacing, usually our depth is always less than 1.2, right? Because 1.2 meters concrete beam is like, oh, it's like huge, right? That's what usually it's like a little way smaller, like something like that. So you're gonna have to check your spacing. So the spacing that the spacing that we assumed earlier down here, we're gonna have to check if it's less than the minimum of these three. This S dash max is from down here. Yeah, it's a weird formula. So, usually minimum is always 300. Yeah. So that's why having a spacing between 200 and 300 is pretty common. Like I've only seen spacing of like for shear we go 200, 300, 150. Is it Randall?
Right.
Yeah, but it's Randall as well. Randall Hansi, yeah. Wow. Yeah, it's cool as Randall. Anyways, yeah, you do your spacing check, which is usually really easy. Web crush, that's the same. Oh, VUS max. Oh, I think I've missed that. Sorry. Yeah. Oh, it's just VU max. Sorry, I've got my notes wrong. This should be VU max. Yeah, you want to check this as well. Your stirrups check. You want to pretty much whatever ASV you have after you've checked your spacing, all that. Make sure it's greater than ASV min over S up here, and you do your final check, which I've actually put up here, and you're done. That's shear. Next week I'll go through an example to kind of explain, kind of solidify it. So, but I guess yeah, I just went through. I think what I'll do from next week, Henry will explain the theory, and I'll just go through questions. I think that would be way better. Because like I think in 1 hour I can't go through a question in theory, so I'll just go through a question, like a past paper question, so you guys are better prepped for the finals. So you go through questions. Like I'm gonna like as I do my questions, I'm gonna have like the steps still there, so I can explain each step. But yeah, I'll end it there. Thank you. Bye.